Welcome back to ECE 441A, 541A. If you haven't performed the pre-quiz, this is a gentle reminder, it's only in red, that it was due last Friday. You can probably still submit it if you haven't taken it. Homework 1 is due this Friday, so if you haven't looked at homework number 1, I would strongly recommend that you start looking at it, and it should be more straightforward now that we've covered the approach to finding equations of motion for a rectilinear or a linear mass spring damper system. What I want to do today is simply very quickly go over these first two items. We'll review the approach that you can follow to derive these dynamic equations. We will go through the three-mass system dynamics derivation very quickly, sort of showing you the steps, and you'll just see that, and it will just flow in front of you like a movie, but you'll at least see a visual as we're talking about these equations. And then we'll get into the, let's say, new material for this lecture, which is finding a state space representation, and I quote the A because a state space representation is not unique for a given system. We could maybe have 30 different state space representations on the exam for one given problem, and they might all be correct. It's a nightmare to grade, but it might all be correct. And then we will look at a very classical block diagram and derive the transfer function for that to get us up to speed so that we can simply go back and forth between a state space representation, differential equations, transfer functions, block diagrams, all of those you need to be comfortable going back and forth between. In terms of deriving dynamic equations, it's helpful to sketch the system, then identify what variables are important, which ones you need to look at, position and velocity in a mechanical system. In an electrical system, it's probably going to be Eli and Ice tell us what. Probably currents in inductors and voltages on capacitors are probably good variables to be writing your equations in terms of. For this mechanical system, we then sketch free body diagrams with the forces identified. We simply move the masses in the appropriate direction of the variables that we just identified. Then we define the forces through their physical relationships, springs being spring constant times displacement, dashpots being dashpot coefficient times velocities. And we'll talk a little bit more about that, I think, as we get into the specific example of the three-mass system. Then you can write the equilibrium equations, which are just algebraic relationships in one dimension for those free body, or based on those free body diagrams, and substitute the force equations that you just found above. Here's the system that we have been working on. It has three masses, but we've also identified a fourth point in between spring 2 and dashpot 2 that can actually move independent of mass 1 and mass 2. If we fixed mass 1 and mass 2, you could still move that point between the spring and the dashpot, independent of having those two masses, mass 1 and mass 2, locked in place or fixed. That means we need to keep track of that point because it could move independently of mass 1 and mass 2. Now, keep in mind when you're writing these equations later, what's happening relative to these different elements. A spring and dashpot, they have two ends. And in some cases, for example, for B sub 3, this dashpot, B sub 3, it's actually fixed on the right, meaning it only has one end that you need to keep track of in terms of its force. The other one is locked in place. Contrast that with spring 2. It has two ends, but they can both independently move, and that's why it's important to keep track of which end is where relative to the other one to give us this positive quantity or this positive result in our equations. I've had some questions on that, and hopefully today or maybe later we will, send back an email to some of the questions. But here's the free body diagram of mass number 1. You simply displace mass 1 in the z1 direction, identify what forces result or are initiated by that movement. Then we simply algebraically, since we're in one dimension or one direction, we algebraically relate those forces. That's our equilibrium equation. And then each of these forces can be expressed in terms of coefficients, positions, and velocities. And if I slide down just a little bit, you'll see that I was running out of room, or I thought I was, and all of that is equal to u sub 1. And that's because u sub 1 is going in the opposite direction to all of the other forces. As I said before, k sub 2, the spring k sub 2, in this equation is the spring constant k sub 2 times z1 minus z sub 4. It's needing to keep track of both ends of that spring. And what you're wanting to do is for this quantity, k sub 2 times some displacement, to be positive in the direction that you've drawn your arrow in this particular free body diagram. If you go back to the original picture, and if you want a force to be positive going to the left, then if you move the left end of spring K2 more than the right end is moved, that's going to compress it in a way that's going to want to go to the left, or Z2 minus Z4 will be a positive number times a positive spring constant, and that will give you a force going to the left. That's where that's coming from. And you can do the same thing with dash pots. It might be easier to sort of treat those as springs and then realize that, oh, these are dash pots. These have to be proportion or scaled by velocities to give us the force. There is the first equation. And one of the key things to keep in mind here is that you now have a Z1 differentiated twice, and you have other variables besides Z1. You have a Z4, you have a Z3. This set of dynamics are coupled with respect to the other masses and elements in your interconnected system. For mass number 2, it's not as involved. It was sort of hanging by itself. You had the inertial force, and you had the force due to the second dash pot, B sub 2, and you then end up with the appropriate red equation. But again, because this is a mass, we have a Z2 being accelerated, or the mass is being accelerated, we have a Z2 double prime. So now we have a Z1 double prime and a Z2 double prime. That's giving us 4 sort of derivatives that we have to keep track of, and that's important when we start to do our state space representation. Free body diagram number 3, or for mass number 3, is a little bit more involved because it had spring 3, dash pot 3, and an externally applied force, U sub 3, going in the appropriate direction. And now the externally applied force is in the same direction as the resulting forces that are created when you displace that mass or move that mass in the positive z sub 3 direction, which is why this equation does not equal u sub 3. U sub 3 is included algebraically on the left-hand side because it's in the same direction as all of the other forces. Finally, for point number 4, I've just represented that as a blob, but now if you displace that in the positive z sub 4 direction, you do have spring 2 and dashpot 2 responding or producing forces as a result of displacing or moving point number 4, and we end up with this fourth equation. Those are our equations, just sort of to reiterate that, and maybe if you review that before you go to bed each night, you're going to start to feel very warm and fuzzy with respect to developing or deriving these. So don't feel too warm and fuzzy and fall asleep now, but tonight, before you go to sleep, it might be a good idea to rehash that or start applying that to homework problem number 1. What we want to do now is put these dynamic equations into a state space representation, which is not unique. And the first thing that we probably want to do is think about the size of our state vector x, which is this tall, thin column. It has n, or Nevada, rows, and Nevada will become more important on on Saturday. You don't have to know what I'm talking about, I guess, if you don't want to. But then it's a column vector. So it's n by 1. We need to know what n is. And I say n and Nevada simply because my n's and m's may not be very well enunciated, and maybe you can say, oh, he said Nevada, that must be lowercase n. Oh, he said Michigan. I guess I could have done Notre Dame and Michigan. But that game's over, so we'll not worry about that. Size of the state vector, little n. What is it for this system? A lot of times for what we're dealing with, it's you concentrate on the highest power derivative of each of the variables. Here we have 2 for z1. We have 2 for z2, and I apologize for those that are watching this. You can't see my fingers. I don't have to do my toes. I have enough digits with my hands. 2 more for z3, and then we have 1 for z sub 4. We then have 7 derivatives to keep track of. Little n is now giving us a vector x that's 7 rows tall and 1 column wide. So our system order is equal to 7. And what we're wanting to do in this state space representation is find the A matrix, which is our system matrix, the input matrix B, and then we will typically have some way of observing or measuring the information contained in that system, and that's our output equation. That's now this C times the state vector plus D times the input vector. In our particular system, we've already determined that x of t, which is a function of time, is now a 7 by 1 vector. And in that column, we will try to include all of the variables in our system dynamics that we need to keep track of, such that when we differentiate them once, we will actually recover all of the dynamic equations that we had. Which means we have to keep track of position and velocity of z1, or mass 1, mass 2's position and velocity, etc. What is the dimension of our input? and now we're simply asking how many different inputs, external inputs, are we applying to this system. If you were looking at a circuit, it would be how many sources do you have, for example. Here we simply have U sub 1 and U sub 3. We have two inputs. Our input vector, U of t, is now 2 by 1. Here's where you can see that the non-uniqueness comes into play. We now need to build up 7 components in the state vector x. And this could be somewhat arbitrary in terms of the ordering. Let's just let the first component, x1, be the position of mass 1, z sub 1. And let's let x sub 2 be the velocity of mass 1. So that we need an equation for the acceleration of mass 1, and we'll get that when we differentiate x sub 2. We don't have to go any higher in the z1 variable in terms of differentiating, because we can capture all of the details that we need by differentiating x sub 2 once. And that's what we're doing here. We want to differentiate all of our state variable components once, and that's now equal to some linear combination of all of the state variables plus some inputs. If that's our strategy, let's go ahead and then say x sub 3 is equal to z sub 2, x sub 4 is equal to z sub 2 prime, and I'm trying to collapse this, so I left off the arguments, but those are all time dependent variables. X sub 5 is now z sub 3. X sub 6 is the derivative or the velocity of mass 3. And finally, we need to keep track of the position of that blob, or that fourth point, z sub 4, because we had an expression for the velocity or the derivative of z sub 4, or the velocity of that point. Those are the state variables. That's how we are going to stack our components in the state vector. Now, I didn't identify outputs. Let's just select some for illustration purposes. Let's say that for an output in this particular problem, we'll just select the positions of the 3 different masses. That means that y of t, we usually just write it as y of t, but that's now collapsed down into, we had 3 masses, so we're now identifying 3 different outputs. Y sub 1 is going to be the position of mass 1, which was z1, but we've called that in terms of a state variable x sub 1. Y sub 2, the second output that we're saying we're interested in as an output, was the position of mass 2, and that we were calling x sub 3 in terms of our state variables. Finally, the third output we said is the third mass position, which in our way of describing or defining the state variables is now x sub 5. That is now, the output is a 3-dimensional vector. It's 3 by 1. We have 7 states, 2 inputs, and 3 outputs. And now if somebody wanted to sketch the sort of picture of our state space representation, we could think of x prime of t is this tall vector that's 7 rows tall. It's 1 column wide. That's now equal to the system matrix A and this guy is 7 columns wide and 7 rows tall. It's square. That now gets multiplied by the state vector x of t, which is again 1 by 7. I'm sorry, 7 by 1. We usually say rows first by columns. Then we have our input matrix, and I may cheat because I have an infinitely wide piece of paper, effectively. I can just keep scrolling over, but I'm going to have to squeeze this in. It has to be compatible with the state vector. We know it has to be 7 tall, 7 rows tall. And how wide is B? Now if you can't see it, you go, well, it has to be compatible with my input vector. My input vector is 1 column wide, but how many individual inputs did we have? We had 2, so we know U is 2 tall, TWO, which means that the B matrix is 2 columns wide. Our B matrix is 7 by 2. This is our input matrix. And that contains all of the dynamics. And what we have to figure out is we have to determine what all 49 variables in that system matrix represent, or what those are from our system. We have 14 elements in our input matrix, and we have to find what those 14 elements equal. What's the output equation look like? It's now our output vector y equaling C times x plus D times U. We had 3 outputs. That means C, our output matrix, three rows tall, and how wide is C? It has to be 7. It has to be compatible with the multiplication by the state vector x. How wide is D? It has to be compatible with U, and U was 2 rows tall, so D has to be 2 columns wide. How tall is D? It has to be such that the product of DU gives you a 3 by 1 result, because the left-hand side has to equal the right-hand side. All of this has to be compatible. It now also has to be 3 rows tall. And this is our, what I might call the direct feed-through matrix. We have 49 entries in the system matrix. We have 14 entries in the input matrix. We have 21 entries in the output matrix, and we have 6 entries in the D matrix. That's why you learned your multiplication tables in first grade or wherever you did it. That's just adding up, right? 3, 6, 9. All right. Now, How do we fill in these 49 entries? We know we need to find an equation for x1 prime. That will give us the top row in this system dynamic expression. We're now going to try to fill in the top 7 elements, entries in that top row of the system matrix, and the top 2 entries in the top row of the input matrix by finding an equation for the first derivative of x sub 1, our first state variable component. This is now the derivative of x1 of t, but how did we define x1 of t? We said that was z1 of t, didn't we? So that's now z1 prime, but we can't have primes on the right-hand side. Do we have a way of describing z1 prime in terms of state variables? And in fact, that's exactly what we defined x sub 2 to equal. And we now need to write x1 prime in terms of a linear combination of state variables and inputs. And we have it now. We can say that that's simply x sub 2 of t, which now allows us in the A matrix and the B matrix to complete the top row. We now want to pick off, when we multiply the top row by the state vector, we need to pick off the second entry, which says, oh, we can do that by just putting a 1 right there, and now we have to count to 7, right? There's 1, 2, 3, 4, 5, 6, 7. That's our top row. 7 of those 49 are pretty easy to find. What's the top row in the input matrix? Did we have any u's present in our x1 prime equation? We have x1 prime is equal to x sub 2. There is no u. The top row of B is now all 0. Questions on that? That's the easy one, if you remember how you defined z1 prime. Now let's look at x2 prime. That's z1 double prime, because it was x2 was z1 prime, so x2 prime is z1 double prime. And now we have to find an equation for z1 double prime, and that's why I wrote all of these down again. There is an equation for z1 double prime if we pull all the terms to the right and divide by m sub 1. If we do that, we will have z1 prime, or z1 double prime is equal to minus b1 over m1 z1 prime minus k1 over m1 times z1 minus k2 over m1 z1. Do you see where all of those are coming from? And eventually we will have plus 1 over m1 times u1. Let me see if I can write that down. Actually, I'll cheat because I have notes. But z1 double prime is now minus k1 over m1 z1 of t minus b1 over m1 z1 prime of t minus k2 over m1 z1 of t. And it just keeps going and going, plus k2 over m1 z sub 4 minus k sub 3 over m1 z1 plus k sub 3 over m1 z sub 3 plus 1 over m1 u1. Whew. Those are all the terms, hopefully, that result when we solve that first set of dynamics, the M1, Z1 double prime, keep that on the left, put everything else on the right, divide by M1, and we should have M1s floating around in the denominator of all of these terms. We can collect common pieces, so we now have x2 prime is equal to several things scale z1. We have a minus k1 over m1. That's this guy. We have a minus k sub 2 over m1. That's that one. Minus a k sub 3 over m1. That's that one. All times z1 of t. Then we have a minus b1 over m1 z1 prime of t plus a k sub 3 over m1 z sub 3 of t that's that one, plus a k sub 2 over m1 z sub 4 of t, that's that one, plus 1 over m1 u1 of t. But we don't want z's and z1 primes. We need x's, and only x's, and no primes on the right-hand side. We now need to go back to how we defined our state variables and substitute those state variable components into the appropriate location as to what they correspond to on our z's. Z sub 1, that was simply what we were calling x1 of t in our state variable. That was the position of mass 1. The velocity of mass 1, which was z1 prime, was x sub 2. Z sub 3, that was the position of mass 3, which was quite a ways down in our state vector. That was x sub 5 of t. Z sub 4 was the last state variable component that we defined. That was x sub 7. Now, if you had a spring constant K1, a spring constant K sub 2, and a spring constant K sub 3, in the labs those might be 800, 500 newtons per meter. Newton. Everybody know what a newton represents, or did anybody bring your lunch? Do you have any fruit in that lunch? Do you have a medium-sized apple? That's about 1 newton. That produces about 1 newton of force in this room. So now if you had a spring that had a spring constant of 400 newtons per meter, if you put 400 apples on top of that spring, it would compress a meter. Okay? You get the visual? So if you don't have a meter of compression, you had a half a meter, well, you need 200 apples. That might get kind of expensive to be compressing that spring, but we could feed this class about 3 times, all right, with 200 apples. So if you all brought in 3 apples on Wednesday, get this visual? We put them on top of this spring that had a spring constant of 400 newtons per meter. We would compress that spring by a half of a meter. Is that okay? All right. You have all those apples. No, you have all those springs. You have some mass, mass 1. You divide by that, and that will just be some number which is scaling x sub 1. But x sub 1, we are now in the second row of our system equation, x2 prime. This coefficient that has 3 terms in it is actually going to be located where in our system matrix? It's going to be in the second row, so I'm going to call that little a, second row, and in what column? Well, it's pulling off or getting scaled by the first state vector component. That will be in the first column of our system matrix. That's the A sub 2, 1 entry out of all 49 entries in that system matrix, A. Whatever that number ends up being, let's say it ends up being minus 600. Minus 600 would be in the 2, 1 entry of that system matrix A. Is that making sense? Where is this guy going to be? And it's going to be a minus B1 over M1. That's the dash pot coefficient. That's a pretty ugly B, isn't it? That's not much better. But B1, M1, B1 divided by M1, where will that be in our system matrix? That's in the 2, 2 entry. Second row, second column, because it has to be scaled by x sub 2. What about this coefficient? K3. Let's say K3 was 300 newtons per meter, and let's say M1 was 1. That's now 300. Scaled by x sub 5, it has to be in the second row, fifth column. This one, A27. This guy, 1 over M1. If we said mass 1 was 1, that's just 1. That's in the input matrix, second row, first column. Which means we can now put in another row in each of our input matrix, our system matrix and the input matrix. The top row wasn't too involved, was it? But now we had a non-zero A21, we had a non-zero A22. What else was non-zero? We had an A25, so that's 0. This one's 0. We had an A25, 0, A27, and here we had a B21, 0. On your exam, when you have a 10th order system, your A matrix will be how big? 10 by 10. It has 100 entries. You'll have 40 minutes for your exam. No, you have 50 minutes unless you come in late. So set your alarm. But do you see the process? Do you get how to do this? Is this a piece of cake? Now you would fill all of these 49 entries in for this 7 by 7. And those are just numerical values once you have given springs, masses, and dashpot values. And the input matrix is likewise. What's the output matrix going to look like? That one's pretty easy. We have 3 rows and we have 7 columns. What are the entries in the C matrix? Did everybody get too warm and fuzzy on my earlier stuff, and so you've fallen asleep? I don't hear any response. What's in the top row of C? The first output, somewhere back here, we said Y1 was X sub 1. the first row needs to, when we multiply everything out, CX plus DU, those matrix products need to result in ending up with an X1 by itself. Now I ask you, what's in the top row of the output matrix? Is that right? What about the D matrix? There were no inputs, were there, in X sub 1 of T? What about the second row? That was X3. The third row was X5. If you're good at making zeros, you make quick work of the output matrix and the direct feed-through matrix. There is no direct feed-through matrix. There is. It's all zero. Questions on the state space representation. That's one way of representing the system dynamics of a system, be it an electrical circuit, a mechanical circuit, an electromechanical system, etc. Questions on that? Now what we want to do is some block diagram algebra. Do you see, if we looked at this, if we put this system, this three-body or this three-mass system, into an all-integrator block diagram, how many integrators would we have on our page? If we drew an all-integrator block diagram, how many integrators would we have? 7. And we would have summing junctions in front of each of those integrators. We would have an X1 prime in front of that first integrator block. And then we would feed back to that whatever this top row indicated. It would only really have one signal going into that, X1 prime. Let's see what happens for a very classical block diagram, and we will collapse a lot of our information into a system transfer function. Let's just say that we have a transfer function, G of S, and we are going to put that in a feedback configuration. Here is our output, Y of S. Here is our reference input, R of S. We are going to compare that reference signal. Maybe that's saying turn this satellite dish to 20 degrees. That might be our reference command. And we would like that satellite to move. So we would maybe like Y, maybe H is 1. We would maybe like Y to go to 20, and we would have 0 air between this filtered output in general, which is H times Y, and the reference input R. What's the overall transfer function in terms of G and H between R and Y? And this is something that we would say, oh, what's the closed loop transfer function in this classical block diagram configuration? We want to know what is T of S, which is the ratio of the output to the reference input. What is that? And as we said before, one way to work through these problems, and typically they will be a little bit more involved maybe than this diagram, but a lot of times it's helpful to start by writing equations for the outputs or the output signal of your summing junction. And keep in mind that there's many things going on here. G and H represent systems. R, E, and Y represent signals. And those are not the same. You brought in apples, now you're bringing in oranges, and you can't combine those. You can't add G to R. That doesn't make any sense. You're saying take a system and add it to a signal. No. You combine signals, you can maybe combine systems, but you can't intermix them. So you want to make sure that when you're adding things up that it makes sense. Let's write the equation for E of S. I hope that it's clear that that's just going to equal all of the inputs into that summing junction, which is R of S minus H of S, Y of S. E of S now is equal to R of S. The output of that summing junction is equal to the input minus H of S, Y of S. Ooh, what happened to my summing junction? Somebody got hungry. Talking about apples and oranges. We all got hungry, didn't we? Oh, what happened to my system? Bottom fell out. Must have been unstable. Sorry. I have to stay awake. Now, what else do we need? We need to write this. We need Y's and R's in this equation in order to solve for the ratio of Y over R. But we can see that Y of S, the output, in this block diagram, there, they came back, didn't it? So now it's really got a bottom on it, that block. But it's now Y is G of S, E of S. And if we simply combine those, we now have Y of S is equal to G of S, but we've already defined E of S to be R of S minus H of S, Y of S. Or now we have G of S, R of S, minus G of S, H of S, Y of S. And let's combine the Y's and the R's, or isolate those on their respective sides. And we now have Y of S plus G of S, H of S, times Y of S is equal to G of S, R of S. Let's assume that we have a single input, single output system. What does that mean? R of S is now a 1 by 1. It's a scalar. Y of S is a scalar. It's 1 by 1. That means G and H are just a scalar transfer function. G of S is some ratio of polynomials in S. H is likewise. And that allows us to divide by those. But if we now combine this, we now have 1 plus G of S, H of S, times Y of S is equal to G of S times R of S. And we're combining signals. We have a system times a signal, which gives us a signal. System times a signal, which gives us a signal. These are all signals. We can now find Y of S is g of s divided by 1 plus g of s h of s. All of that is times r of s, and there is our transfer function that we were seeking. There is our t of s between r of s and y of s, and now somebody could just put a block diagram t of s between r of s and y of s. We'll pick up Wednesday with trying to interrelate all of these different system representations and be able to go back and forth between them.